And if the thrust-to-weight ratio, or TWR, is the measure of a rocket engine's raw strength, then specific impulse, or ISP, is the measure of its intelligence. In the high-stakes theater of orbital mechanics, strength is a prerequisite, but efficiency is the savior. To understand the Raptor 3 specific impulse, one should look past the powerlifter analogy of the previous section and instead consider the world-class marathon runner. This is an athlete who can traverse vast, grueling distances on a single energy bar, not because they possess more energy than their competitors, but because their body consumes every available calorie with surgical, almost obsessive precision. And in the vernacular of aerospace engineering, specific impulse is the rocket scientist's miles per gallon. It defines how much bang you get for your buck, where the buck is every kilogram of propellant hauled off the launch pad. In a universe governed by the cold, unyielding tyranny of the Tsiolkovsky rocket equation, ISP is the only variable that allows us to cheat the exponential growth of propellant mass. Without high ISP, the dream of a multi-planetary species remains exactly that, a dream. And the dimensional logic of seconds to the uninitiated, the unit of measurement for specific impulse, the second, can be deeply counterintuitive. Why would a measure of fuel efficiency be expressed in time? And the mathematical elegance of ISP lies in its derivation. If you define thrust as the force produced by the engine and divide it by the mass flow rate of the propellant, multiplied by Earth's gravity, g sub 0, to standardize the units, the kilograms and newtons cancel each other out, leaving only time. In practical terms, specific impulse represents how many seconds a single pound or kilogram of propellant can produce a single pound or kilogram of thrust. And if an engine has an ISP of 300 seconds, it means that 1 unit of fuel can provide 1 unit of thrust for 5 minutes. If you can push that number to 350 or 380 seconds, as the Raptor 3 does in various configurations, you are not just making a better engine, you are fundamentally altering the mission architecture. You are increasing the delta V, the total change in velocity available to the spacecraft, without adding a single gram of extra weight. In the computer science perspective, ISP as big O efficiency. For the graduate in computer science, the most effective way to conceptualize specific impulse is through the lens of algorithmic complexity, or big O efficiency. N, consider a sorting algorithm. If you have a dataset of 1 million items, an O of n squared algorithm is a brute force approach. It will eventually finish the task, but it will consume an enormous amount of compute time and energy to do so. Conversely, an O of n log n algorithm is efficient. It achieves the same output, a sorted list, with significantly less input, or CPU cycles. And in this framework, propellant is your memory overhead, and thrust is your output. A low ISP engine is an inefficient algorithm with high space complexity. It requires a massive memory leak of propellant to perform a simple task. The Raptor 3, by contrast, represents an optimized kernel where the instruction overhead of combustion is minimized. And by achieving a higher specific impulse, SpaceX engineers have essentially optimized the internal loops of the engine's thermodynamics. They have moved the engine from a brute force approach to propulsion toward an algorithmic approach, where the goal is to extract the maximum amount of kinetic work, or forward movement, for the minimum propellant expenditure, or resource cost. In the code of the cosmos, ISP is the coefficient that determines whether your mission scales to Mars or times out in low Earth orbit. And the physics of exhaust velocity, the input vs. output logic. To understand how the Raptor 3 achieves its record-breaking efficiency, we must look at the relationship between specific impulse and exhaust velocity. The fundamental law of rocketry is simple. The faster you can throw stuff out the back, the faster you go forward. And specific impulse equals exhaust velocity divided by gravity at sea level. This equation tells us that specific impulse is directly proportional to the velocity of the gases exiting the nozzle. To increase specific impulse, you must increase the kinetic energy of the exhaust stream. In a chemical rocket, this kinetic energy comes from the heat and pressure generated in the combustion chamber. And the Raptor 3 high specific impulse is a direct consequence of its full-flow staged combustion cycle. As we explored in Chapter 4, the full-flow staged combustion cycle ensures that 100% of the propellant, both the liquid oxygen and the liquid methane, enters the main combustion chamber as a high-pressure, high-temperature gas. And in a traditional open-cycle engine, like the Merlin 1D, a portion of the propellant is burned in a gas generator and then dumped overboard to drive the turbopumps. This is wasted propellant. It contributes almost nothing to the thrust of the vehicle. In computer science terms, this is dead code or leaked memory. The Raptor 3 eliminates this leak. Every molecule of propellant that enters the engine is utilized to generate thrust. By turning the waste heat of the turbopumps back into the main chamber, the Raptor 3 achieves a nearly perfect input-to-output conversion, maximizing the exhaust velocity and, by extension, the specific impulse. And the chemistry factor, why methane is the efficient variable, the choice of propellants, discussed in Chapter 2.1, is the primary constant in the ISB equation. While hydrogen LH2 offers a higher theoretical ISB, roughly 450 seconds, it is notoriously difficult to handle, requiring massive, heavily insulated tanks due to its low density. And methane, CH4, the fuel of the Raptor 3, represents the golden mean of rocket chemistry. It offers a higher specific impulse than the kerosene, RP1, used in the Falcon 9, but without the technical debt associated with hydrogen. And the high specific impulse of the Raptor 3 is specifically aided by the molecular weight of its exhaust products. According to the laws of thermodynamics, exhaust velocity is inversely proportional to the square root of the molecular weight of the exhaust gases. Methane combustion produces a mix of water vapor and carbon dioxide. Because methane is hydrogen-rich, its exhaust is lighter than the soot-heavy exhaust of a kerosene engine. And this molecular optimization allows the Raptor 3 to maintain a high exhaust velocity even at the extreme pressures of 350 bar. When combined with the gas-to-gas mixing discussed in Chapter 4.2, the combustion is so complete and so uniform that the engine approaches the theoretical limits of chemical efficiency. There is no unburned fuel leaving the nozzle. There is only a high-velocity, high-temperature kinetic stream. In the step-by-step math of propellant savings, to truly appreciate the impact of a few seconds of specific impulse, one must look at the mass fraction of a rocket. For a vehicle like Starship, which aims to be fully reusable, the margin for error is razor-thin. And let us perform a thought experiment. Imagine a Starship-sized vehicle attempting to reach Mars. If the engine has a specific impulse of 330 seconds, typical for a high-performance kerosene engine, the propellant tax required to reach a certain velocity might leave only 50 tons of room for payload. If you increase that specific impulse to 350 seconds, the Raptor 3 sea-level target, the efficiency gain reduces the required propellant mass significantly. That saved mass does not just disappear, it is converted directly into payload. If the vacuum-optimized Raptor 3 achieves 380 seconds, the delta-V capacity increases exponentially. And this is the compound interest of rocketry, because you have to carry the fuel you haven't burned yet. Any increase in efficiency at the beginning of the burn results in massive savings at the end of the burn. A 5% increase in ISB can lead to a 20 to 30% increase in payload capacity for deep space missions. In the context of a Mars colony, this is the difference between sending a skeleton crew and sending a fully equipped industrial base. And thermal efficiency, managing the energy overflow high ISB is not free. To get high exhaust velocity, you need high temperatures. The Raptor 3 operates at temperatures that would liquefy most industrial metals instantly. This creates a thermal bottleneck. If you can't manage the heat, you can't run the engine hot enough to achieve high ISB. And SpaceX engineers solved this through regenerative cooling, but with a full-flow twist. In the Raptor number 3, the cryogenic methane doesn't just sit in the tanks. It is routed through microscopic channels in the engine walls before it is burned. It acts as a heat sink, absorbing the thermal energy from the combustion chamber. And this serves two purposes. It keeps the engine from melting, which provides structural integrity. It preheats the fuel, turning that absorbed thermal energy back into kinetic energy during combustion, which provides thermal efficiency. And in a computer science context, this is akin to heat recovery in a data center, where the thermal output of the servers is recycled to provide power or heating for the facility. By closing the thermal loop, the Raptor number 3 ensures that almost no energy is lost to environment. The heat that would normally be a bug or a destructive force is refactored into a feature, which is a boost in exhaust velocity. In the perfect mix, gas-to-gas combustion and ISB stability. One of the greatest enemies of specific impulse is combustion instability. If the fuel and oxidizer do not mix perfectly, you get pockets of uneven temperature and pressure. This creates turbulence in the exhaust stream, which acts as friction, slowing down the exhaust velocity and dropping the specific impulse. And traditional liquid-to-liquid engines struggle with this because mixing two liquids at high pressure is like trying to mix oil and water in a hurricane. However, because the Raptor 3 is a full-flow engine, it mixes gas to gas. And when hot gaseous oxygen meets hot gaseous methane, the mixing happens at the molecular level almost instantaneously. This results in a laminar combustion profile. The flame front is stable, the pressure is constant, and the exhaust flows through the nozzle with minimal entropy. From an efficiency standpoint, this is the hardware equivalent of a zero-weight state in a processor. The engine does not have to wait for the fuel to vaporize or mix. The energy release is immediate and total. An ISB in the vacuum. The expansion ratio advantage. It is important to distinguish between the ISB of the Raptor 3 on the launch pad and its ISB in the vacuum of space. As we will see in the next section, the atmospheric backpressure of Earth's air pushes against the exhaust, effectively clogging the nozzle and reducing ISB. And at sea level, the Raptor 3 is a beast of burden, fighting through the thick soup of the atmosphere. But once Starship reaches the vacuum-optimized Raptor vac variants take over, with larger nozzles that allow the exhaust gases to expand to near zero pressure. The specific impulse jumps from approximately 350 seconds to approximately 380 seconds. And this jump is what makes the Starship architecture viable. The high ground-level ISP gets the vehicle off the pad, but the vacuum ISP is what provides the endurance for the long transit to the Moon or Mars. It is the transition from a sprint to a long-distance cruise, made possible by the same fundamental engine architecture. And the economic implications of high ISP. Finally, we must consider the macro efficiency of specific impulse. In the era of expendable rockets, ISP was a secondary concern to reliability and cost. If you are only going to fly the engine once, you do not mind if it is a bit of a gas guzzler, as long as it gets the job done. But Starship is designed for rapid reusability. If you are flying 10 times a day, the fuel bill becomes a dominant factor in your OPEX, or operating expenses. A higher ISP means you need less propellant per kilogram of payload delivered. And more importantly, it means you need less tankage. A more efficient engine allows for a smaller, lighter ship, which in turn requires less thrust to move, creating a virtuous cycle of lean design. The Raptor 3 ISP is not just a technical achievement, it is the cornerstone of SpaceX's business model. It is what allows them to lower the cost per kilogram to orbit by orders of magnitude. And the limits of chemical propulsion. The Raptor 3 likely represents the end of the road for chemical ISP. We are approaching the point where we are extracting nearly 99% of the theoretical chemical energy available in the methane-oxygen bond. To get significantly higher ISP, in the range of 800 to 2,000 seconds, we would need to move to nuclear thermal propulsion or ion drives. But for the task of lifting thousands of tons of steel and human life out of a deep gravity well, chemical propulsion remains the only viable high-thrust solution. And within that domain, the Raptor 3 is the undisputed master of efficiency. It has taken the messy reality of fire and pressure and turned it into a clean mathematical certainty. However, having a high exhaust velocity is only half the battle. To turn that velocity into actual thrust, you must shape the flow. You must take that chaotic high-pressure gas and direct it with absolute precision. This is the realm of geometry, where the invisible hand of physics meets the sculpted curve of the engine's exit. And to understand how the Raptor 3 translates its internal efficiency into external movement, we must examine the final stage of the journey, the point where the gas leaves the machine and enters the void. In 6.4, the math of the bell, why the nozzle shape matters.